Hello everyone, welcome to Sai Tutorials Jamkandi. So in our class, 10th class Kannada medium and English medium, 8th, 9th Kannada medium and English medium, maths, science, English classes are available in regular classes as well as in the online classes. So please join us and learn the things accurately. So, dear students, I'm going to handle the second PUC physics chapters. So, I have completed three chapters till now. So, I'm going to start the new chapter of your syllabus, that is fourth chapter, moving charges and magnetism. Okay. So, in today's session, let us discuss about the introduction part related to the moving charges and magnetism. Okay. So, you all know about charges and all. Okay, so how these charges are going to be uh, how these charges are going to be in the form in the application of magnetism. Okay, so form. Now the introduction part related to your syllabus, that is introduction. Okay, introduction part of today's session, that is moving charges and magnetism. See, first of all, more than 200 years ago, electricity and magnetism are separate branches here. So, in 2000 years back, 2000 years till now, electricity and magnetism are are separate branches. So now in 1824, Oersted, he made the connection between the electricity and magnetism. So back to 2000 years, we have learned that electricity and magnetism are separate branches, but in 1824, Oersted is one of the scientists. He made the connection. He made the connection in between the electricity and magnetism. Okay, electricity and magnetism. So let me derive some of the concepts related to the what Oersted has derived, did an experiment on electricity as well as on magnetism. So let us discuss one by one. This is a just deep introduction part about your moving charges and magnetism. See, Oersted is one of the scientists who derived the relationship between electricity and magnetism. So what he told, let us discuss. So let us discuss about Oersted experiment. Just the introduction part. So if what he did, let us see. So in current carrying wire, so suppose if you consider any current carrying wire, if current is moving from point A to B, so let us consider this is the wire. Okay, so this is point A and this is point B. Okay, suppose in current carrying wire, if current is moving from point A to B, the north pole of the magnetic needle is deflected towards the west direction. Okay, so this is west and this is east, this is north and this is south in magnetism. Do you all know this? Am I right? If current is moving from point A to B, if a current is moving from point A to B, okay, the north pole of the magnetic needle deflected towards the west direction. Sorry, this is let me write again. See, suppose let us consider this is point A and this is point B. Okay. So this is west direction and this is east direction, and the magnetic needle having north pole and south pole. Okay. Now, suppose the current is moving from point A to B. Is it or not? From point A to B. So the north pole is deflected towards the west direction. Is deflected towards the west direction. If current direction is reversed, I mean from B to A, the north pole of the magnetic needle deflected towards the east. Okay, this north pole is deflected towards the east direction. So if current carrying wire placed very near to magnetic needle, the deflection increases. Suppose if this current carrying wire is placed near to the deflecting material, okay, deflecting magnetic needle, so the deflection will be increases. The deflection will be increases. Is it or not? Okay. The deflection in magnetic needle is arranges due to magnetic field produced by current carrying wire. So, uh, see the deflection. So, whatever the deflection happens here in the magnetic needle, it will all due to the arrangement. It will all due to the arrangement due to the magnetic field produced by that current carrying wire. Okay, whatever the current carrying wire that will produce a magnetic field, so that magnetic field is going to happen the deflection in that particular material. So, okay, so let us discuss one by one. So what is the first point here? In a Orsted experiment, in current carrying wire, please note down, in current carrying wire, if current is okay, if current is moving from A to B, the north pole, okay, pole, the north pole of the magnetic needle deflected towards west direction. So west direction, this is one point. And also suppose in reverse, if current is reversed, okay, if current direction, if current direction direction is reversed, that is from point B to point A, the north pole of the magnetic needle deflected towards, please note down it, towards east direction. So this is what the experiment. So when the magnetic deflection, when the deflection will increases, when that current carrying wire is placed near to the magnetic needle, so the deflection will increases. So this is all about the Orsted experiment. I hope this concept is clear to you. Now coming to the concept, okay. See, coming to the introduction part of the moving charges and magnetism. See, a gravitational field, okay. A gravitational field is associated with the mass, of course. Is it or not? The gravitational field is associated with a mass. And an electrostatic field is associated with a charge. I have discussed in the earlier classes. Okay. See, the gravitational field is associated with the mass and electrostatic field is associated with the charge. Then what about magnetic field? So it is a region surrounding the current carrying conductor. It is a region. Okay, whatever the region that surrounds the current carrying conductor, it is the magnetic field. It will depend on the region surrounding a current carrying conductor. So this is first point. So an electric charge causes an electric field. Is it or not? An electric charge causes an electric field which will affect an electric charge. Affects on which? On charges. Okay. And now a moving electric charge. Okay, a moving electric charge, I mean electric current, this will causes the magnetic field. I have told you, when the current carrying any type of conductor, okay, it is placed near to the magnetic field, okay, and magnetic needle, the deflection will increases, I have told you. So in the same way, the moving electric charges or electric current causes the magnetic field with that will show the deflection. So that will affect the moving electric charge, okay, that will affects the moving electric charge. Of course, the charge electric charges are moving here, the current is flowing in the conductor, so this will produces the magnetic field. That magnetic field affects on which phenomenon? Only on a moving electric charges, on a moving electric charges. So this is all about the just a part of introduction. Okay, now coming to the concept. Okay. Magnetic force, magnetic force on charge placed, magnetic force on a charged particle moving in a magnetic field. Okay, magnetic force on a charged particle moving in a magnetic field. You can divide three concepts here. Okay, see, magnetic force is one thing, charged particle is one thing, and a magnetic field is one thing. So totally magnetic force on a charged particle moving moving in magnetic field. Okay, this is the first thing. Magnetic force, see, I'm applying here a magnetic force on which? On a charged particle, on a charged particle moving in a magnetic field. Okay, there will be a magnetic field. Now coming to the picture, see, force on a moving charge, the diagrammatic part, this is a diagram you can see here. Now, the force exerted by a magnetic field on a moving electric charge or a current carrying conductor is called as a magnetic force. The first thing is magnetic force. Now, whatever the force, okay, whatever the force exerted by which? By magnetic field, okay, by magnetic field on a moving electric charge, on a moving electric charge or a current carrying conductor, it is called as a magnetic force. So first of all, I have said you that there are three concepts in this line. Is it or not? Magnetic force, a charged particle, moving in magnetic field. Suppose if you consider these three phenomena, you can define the definition of magnetic force. Is it or not? So see here, the force exerted, the force, this is the force exerted by a magnetic field, okay, magnetic field on a moving electric charges, on a moving electric charges or a current carrying conductor is called as a magnetic force. Okay, this is the force on a moving charge, the force exerted by a magnetic field on a moving electric charges or a current carrying conductor is called as a magnetic force. Suppose the charge q, suppose the charge q, here they have considered the charge q. Okay, a charge q moving with a velocity v bar and a magnetic field b bar and experiences a force f bar. So totally it is given by f is equal to f bar is equal to q, the charge q into velocity v bar cross b bar. This is the expression for the magnetic force. Okay. See, the force exerted by a magnetic field on which? On a moving electric charge. So they have considered charge as a Q. And also the magnetic field, that this is B bar. Okay, magnetic field is B bar. So the force is equal to the charge Q with a moving velocity V bar, and magnetic field B bar experiences a force. So that force is equal to F bar is equal to Q into V bar in cross B bar. So this is the expression for magnetic force. Okay. Now, the magnitude, if you write this force, magnetic force in case of magnitude, the magnetic force will become sine theta. F is equal to QVB. If you remove this cross here, if you remove this cross, you will get sine theta. I mean QVB into sine theta. Is it or not? So in magnitude, it can be written as F bar is equal to F not bar, F is equal to QV into sine theta, where theta is the angle between the velocity and magnetic field. Is it or not? Okay. So in magnitude, we can also write it as magnetic force F is equal to QVB sine theta, where theta is the angle between the velocity V bar and the magnetic field. So the direction of force is that of V bar cross B bar. See, suppose here V bar cross B bar is there. Am I right? Not. So the force, that force is always perpendicular to the these two phenomenons. Is it or not? So the direction of F bar is that of V bar cross V bar B bar. So force will become zero. This is clear to you, and this is clear to you. Now F is zero. F is 0 when V is V bar, when V bar is parallel or anti-parallel to B bar. Suppose if you consider this velocity, this is force and this is B bar, then suppose this same V bar it is, or it may be here only. So then at that time V bar, okay, at that time B bar will become 0 degree, that theta becomes 0 degree, or it will become 180 degree, that is straight angle. So in that condition the velocity will become 0 parallel, or when velocity is parallel to or anti-parallel to the B. Suppose this is held above this B bar, or suppose this velocity is held like this, I mean it is at 180 degree, or suppose it will remain at this condition only, it will become 0 degree. So at that condition magnetic field becomes 0 force, then the force will becomes 0. Is it or not? Now force F is maximum. Force F is maximum when a charged particle moves in a direction perpendicular to the direction of magnetic field. Okay, see, this is very very important. The force will become when the charged particle moves in a direction, okay, moves in a direction perpendicular to the direction of the magnetic field. So in that condition F maximum will become QVB into sine 90 degree, the maximum angle, that is 90 degree. So perpendicular means it is perpendicular to, that is 90 degree it will become. So it is maximum. We will say this is maximum. So what is sine 90 degree? It is equal to 1. So the equation will become QVB only itself. Is it or not? Now the work done by the magnetic force, okay, now the whatever the work done by this magnetic force on a charged particle is 0. When it will be 0? When the force is perpendicular to V bar, I mean when the force is perpendicular to V bar. Thus a magnetic field cannot change the speed and kinetic energy of a charged particle. If you consider that if force becomes perpendicular to V bar, then the work done will become 0. That magnetic field cannot change the whatever the speed of the charges moving inside the current carrying conductor, and also the kinetic energy of the charged particle, that will not change anything. Is it or not? If work also itself becomes 0, then force is also 0, then the magnetic field whatever is going, I mean whatever magnetic field applied in the that conductor, that will not change the speed, and kinetic energy of the charged particle. Okay, so these are all about the magnetic force. Okay, magnetic force on a charged particle moving in a magnetic field. So I have discussed here. Suppose the force exerted by magnetic field on a moving charge or a current carrying conductor, it is called as a magnetic force. So the magnetic force, it involves a charge q and velocity v bar of of that charge, and also the magnetic field applied in the current carrying conductor. So experiences the force, that force is equal to charge into velocity cross b bar. Okay. So suppose if you consider in case of magnitude, the magnetic force can be written as F is equal to QAB into sine theta, where theta is the angle between V bar and B bar. So the direction of F bar is that of perpendicular to V bar and B bar. So F is a 0. This means F bar is perpendicular to B bar and B bar is perpendicular to V bar, like that. Okay. F is 0 when velocity is parallel or anti-parallel to the magnetic field. Okay. Magnetic field. So this is all about the uh, magnetic force. So it will be maximum when it will be maximum when theta is equal to 90 degree, or when it is the charged particle moves in a direction perpendicular to the direction of the magnetic field. So in that condition, the magnetic force will become maximum. Okay. In that condition, the magnetic force become maximum. So the total work, if the total work done by the magnetic force on a charged particle is 0, and that at that condition F bar is perpendicular to V bar. So then that magnetic field cannot change the speed of the charges and also the kinetic energy of a charged particle. So this is all about the magnetic force. Now coming to the next concept, Fleming's left hand rule. Very, very important it is. So if you stretch your hand like this, Fleming's left, take your left hand and stretch like this. Fleming is one of the scientists who derived the magnetism in case of the left hand rule. Okay. So now according to the Fleming's left hand rule, the direction of the force, see, you can say here this is thumb. This is forefinger. And this is middle finger. Okay. If you keep this, if you held, if you hold your left hand like this, which three are perpendicular to each fingers, is it or not? This is perpendicular to forefinger and this is perpendicular to this finger, is it or not? Okay. See, here the direction of the thumb will show the force and the direction of forefinger will show the field, and the direction of the middle finger will show the velocity. So here the direction of the force on a charged particle, see, the direction of the force on a charged particle moving perpendicular to the magnetic field, it is given by Fleming's left hand rule. Okay. See the force, this is the magnetic force and this is the magnetic field. This is F bar and this is velocity. Now, stretch the first three fingers of the left hand such that they are mutually perpendicular. Okay. Three fingers. Did you stretch it? Okay. Stretch the first three fingers of the left hand such that they are mutually perpendicular to each other. So if the forefinger is in the direction of the field, the direction of the magnetic field, so if the forefinger is in the direction of the magnetic field B bar, the middle finger is in the direction of the velocity of the positively charged particle, then the thumb gives the direction of the mechanical force. So this is about the Fleming's left hand rule. So by stretching the three fingers, you can easily understand the Fleming's left hand rule. See what Fleming's will tell us that the direction of the force on a charged particle moving perpendicular to each other. Okay. So now stretch the first three fingers of the left hand such that they are mutually perpendicular to each other. If the forefinger is in the direction of the field and middle finger is in the direction of the velocity, now of the positively charged particle, then the thumb will give the direction of the mechanical force. So this is the Fleming's left hand rule. So this is the Fleming's left hand rule. And I have discussed here the magnetic force on a charged particle moving in the magnetic field. There are some cases. Okay, there are some cases. Let us discuss one by one. Suppose I have told you that just a second. Okay, this is the direction of force, and this is the direction of magnetic field B bar, and this is the direction of velocity, and having the angle that is theta. Is it or not? Now we know that F bar is equal to Q V bar cross B bar. So in magnitude it can be written as Q V B into sine theta. Is it or not? Now the direction of the force is always a perpendicular to the plane containing V bar and B bar. So the force, whatever the force applied here, this is always perpendicular to B bar and V bar. So suppose if you consider the case 1, it is very important. So case 1, if theta is equal to 90 degree, so what will happen? F, just a second. F will become QVB sine theta is 90 degree. So it will become F is equal to QVB since sine 90 degree. Sine 90 degree is equal to 1. So in that condition, the force is maximum. I have told you that in that condition, the force is maximum. So this is one case. And coming to the second case, okay. Suppose if theta is equal to 0 degree or theta is equal to 180 degree. So what will happen here? We know that F is equal to QVB into sine theta. F is equal to QVB sine 0 degree is equal to 0. Is it or not? Since theta is equal to 0 degree. Sine 0 degree is 0. Is it or not? And suppose if you consider F is equal to QVB sine 180 degree, it will also become 0 because sine 180 degree is equal to 0. So in that condition, force is minimum. Is it or not? So there is another case. If charge, case 3. Suppose if you consider charge is 0, then force will become 0. Is it or not? So the last case, if velocity is 0, then force will be become 0. So this is the case. Okay. In the magnetic field, okay, magnetic force, that force acting on a moving charge in a magnetic field, that is F bar is equal to Q V bar cross B bar. So if you consider it in a magnitude, it will become QVB into sine theta. So that F is equal to QVB into sine 90 degree. If you consider theta is equal to 90 degree, and if you consider theta is equal to 0 degree or 180 degree, it will become, the force will become minimum. So suppose if the charge flowing inside that conductor is 0, then force also 0. And also if velocity is 0, the force will become 0. So these are some of the cases. Okay. So dear students, today we have discussed some introduction part related to the moving charges and magnetism, and for magnetic force on a charged particle moving in a magnetic field, and Fleming's left hand rule. So in the next session, let us discuss whatever the concept related to your syllabus. I'm going to derive those. So by this, I'm going to wind up the session by today itself. Thanks for watching, and please don't forget to subscribe our channel. Please work out more, and please note down whatever I have said in the class. Don't waste your time and start learning and start preparing for your exams. Thank you, dear students.